9.2, Refraction and Total Internal Reflection. When a light wave strikes a transparent material, such as glass or water, as shown in this diagram below, this is the incident ray striking the surface of glass. Some of the light is reflected at the surface, and we see it with this reflected ray. And the rest of the light passes through or transmits through the material. Refraction is defined as the bending of light as it travels at an angle from one medium to another. The angle of refraction is the angle that a light makes with respect to the normal. And the normal is this line right here that hits the surface at 90 degrees. Different materials have different optical densities. And the optical density of a material is the property of a material that determines how light behaves when it travels through the material. We know that the speed of light in a vacuum is constant. It's one of the most important constant values we know. We give it the symbol c, and c is equal to 3 times 10 to the power of 8 meters per second. In most cases, this is a very good approximation for the speed of light in air. We know that when light travels from a vacuum into air, the molecules in air actually cause light to slow down a small amount. However, when light enters a different medium, it interacts with the atoms, as I mentioned, and the average speed through the medium is changed. The ratio of the speed of light in a vacuum to the speed of light in another medium is called the index of refraction. And the index of refraction is governed by this equation. N is equal to c over v, where c is the speed of light in the vacuum and v is the speed of the material in another medium. We know that when light travels from less optically dense materials to more optically dense materials, that light will bend towards the normal. And the converse is true. When light travels from more optically dense materials to less optically dense materials, it will bend away from the normal. Now, this path is also reversible. We call this the principle of reversibility. And it states that a light ray will follow exactly the same path if its direction of travel is reversed. When solving problems dealing with the index of refraction for light in different medium, we use Snell's law. And Snell's law states that the index of refraction times the sine of the incident angle is equal to the index of refraction for the second medium times the sine of the refracted angle, theta 2. So n1 sine theta 1 is equal to n2 sine theta 2. Similarly, it's important to note that when light passes from one medium to another, the frequency of light does not change. So we know that the index of refraction is also equal to wavelength of light, lambda 1, over the wavelength of light in the medium number 2, lambda 2. So we can say n is equal to lambda 1 over lambda 2, or similarly we can say n1 over n2 is equal to lambda 1 over lambda 2. Let's start looking at some examples. Calculate the angle of refraction for light moving from a vacuum into a plate of glass with index of refraction 1.47. The angle of incidence is 40 degrees. So let's write down what we know. We know the original medium has an index of refraction of 1, and that's because this material is a vacuum. And the index of refraction for a vacuum is 1. We know that the angle of incidence is 40 degrees. We know the index of refraction for glass is 1.47. And what we want to find is the angle of refraction. So we'll use Snell's law, which states n1 sine theta 1 is equal to n2 sine theta 2. Our job is to find theta 2. If we rearrange, we get theta 2 is equal to the inverse sine of n1 sine theta 1 over n2. We can sub and solve. We get inverse sine of 1.0 sine 40 degrees divided by 1.47. If we punch this into our calculator, theta 2 is equal to 26 degrees. Therefore, the angle of refraction for light moving from the vacuum into glass is 26 degrees. In part B, the light continues through the glass and emerges back into the vacuum. Let's calculate the angle of refraction when light exits the glass. So we know the index of refraction for glass is 1.47. And we know the angle of incidence onto the vacuum is 26 degrees. We just calculated that above. We know the index of refraction for the vacuum that it will be emerging from, and I'm going to call this N3, is 1.0. And what we want to find is the angle of refraction as it emerges from the vacuum. Now you can do a bit of a prediction. We're traveling from a more optically dense medium to a less optically dense medium. So we should expect this to bend away from the normal. So its value should be greater than 26 degrees. Let's find out exactly what the angle of refraction is. So we can say n2 sine theta 2 is equal to n3 sine theta 3. And we're solving for theta 3. It's equal to the inverse sine of n2 sine theta 2 over n3. That's the inverse sine of 26 degrees. Apologize. Putting the index of refraction in here, 1.47 times the sine of 26 degrees divided by the index of refraction for the vacuum, which is 1. If you punch this into your calculator, you get an index of refraction of 40 degrees. Now, this should come as no surprise. If light travels from a vacuum to glass at an angle of 40 degrees, then travels through the glass, bends towards the normal, then travels back out of the glass, back into the vacuum, it's going to bend away from the normal. And the principle of reversibility tells us that this path is completely reversible. So if it entered at 40 degrees, it should leave at 40 degrees. So again, this is a bit of a proof of the principle of reversibility. In part C, let's suppose the light exits into water instead of a vacuum. Let's calculate the angle of refraction from light moving from glass into water. And we know the index of refraction for water is 1.33. So we are traveling, N2 is glass, which is an index of refraction of 1.47. We know the angle of incidence from glass to water is 26 degrees. We are now going to exchange the third medium from a vacuum into water, and the index of refraction for water is 1.33. And what we want to find is the angle of refraction when we switch from the vacuum to water. So rearranging for theta 3, we have inverse sine of n2 sine theta 2 over n3. We can sub and solve. That's 1.47 sine 26 degrees over the index of refraction for water is 1.33. Punch this into our calculator. We're traveling from glass into water. Water has a lower index of refraction, so we're traveling from a more dense to a less dense. It should bend away from the normal, so we should expect a value that is greater than 26 degrees. When we punch this in, we see that we do in fact get an angle that is greater than 26 degrees as we move from a more optically dense material to a less optically dense material, and that angle of refraction is 29 degrees. We're going to examine refraction a little bit further with sample problem number 2. Light travels at 3 times 10 to the power of 8 meters per second. Laser light with a wavelength of 520 nanometers enters a sheet of plastic. The index of refraction for the plastic is 1.49. Let's calculate the speed of the laser light in the plastic. So we know that the index of refraction is equal to the speed of light over the speed of light in the new material. So the speed of light in a vacuum over the speed of light in the new material. So if we want to find the speed of light in this new material, it's equal to the speed of light in a vacuum divided by the index of refraction, in this case for plastic. So that's 3 times 10 to the power of 8 meters per second divided by the index of refraction for plastic, which is 1.49. Punch this in and you get a speed of light of 2 times 10 to the power of 8 meters per second. Therefore, the speed of light, of laser light in the plastic is 2 times 10 to the power of 8 meters per second. In part B, we want to calculate the wavelength of laser light in the plastic. We know that the index of refraction is equal to lambda 1 over lambda 2. So in this case, lambda 2 is the wavelength in plastic, and it's equal to the wavelength in air divided by the index of refraction for plastic. So if we punch this in, we get the index of refraction for plastic is 1.49. Now the wavelength of the laser light is 5.2 times 10 to the power of -7 meters. That's 520 nanometers. You need to be able to convert between nanometers and meters. Know that 1 nanometer is 10 to the power of -9 meters. So 520 nanometers is 5.2 times 10 to the power of -7 meters. If you punch this into your calculator, you get a wavelength of 3.5 times 10 to the power of -7 meters. Note that this is also 350 nanometers. The wavelength of laser light in plastic is 3.5 times 10 to the power of -7 meters, or 350 nanometers. Okay, what we want to find in part C is the frequency of the laser light in the plastic. We know from the universal wave equation, V is equal to F lambda, that frequency is equal to V over lambda. We've calculated this new speed up above to be 2.0 times 10 to the power of 8 meters per second. And we know the wavelength in the plastic is 3.5 times 10 to the power of -7 meters, which is 350 nanometers. If we punch it in, we get a frequency of 5.8 times 10 to the power of 14 hertz. So the frequency of laser light in the plastic is 5.8 times 10 to the power of 14 hertz. Next, we'll introduce the concept of dispersion of light and prisms. The speed of the wave depends on its frequency and wavelength. When the wave enters a new medium, its frequency does not change, and we've learned this above. But what does change is its wavelength. This means that the speed of the refractive light depends on its wavelength. This dependence of the speed of light on wavelength causes light waves to separate in a phenomenon called dispersion. And you've seen dispersion. You've seen classic examples of white light traveling through a prism, and when it is transmitted through, it disperses into its constituent wavelengths. So you see the different colors of light emerging at different distances or positions, resulting in a rainbow effect. So the definition of dispersion is the separation of a wave into its component parts according to a given characteristic, such as frequency or wavelength. Another effect of triangular shape of prism is that light rays leaving the prism are not parallel to the light waves that enter the prism. The angle between the incident ray and the final outgoing ray is called the angle of deviation. The following tutorial examines how you can use Snell's law to solve dispersion problems involving prisms. Before we begin, let's define the angle of deviation as the angle between the incident ray and the final outgoing ray after reflection or refraction. Okay. In this sample problem, the figure below shows a ray of light incident on a glass triangular prism. It is refracted as it passes through the first face and then is refracted again through the second face. In part A, we want to calculate the angles of refraction for the blue light and for the red light traveling from air into the left boundary of the prism. The angle of incidence at the left boundary is 40 degrees. The index of refraction for blue light in the prism is 1.47, and the index of refraction for red light is 1.46. The index of refraction for air is 1.0003. So we're going to do two examinations here. We're going to look at blue light, and we're going to look at red light. So we want to find the angle of refraction for blue light at the left interface, which is this interface right here, and the index of refraction for red light along this same left interface. So I'm rearranging Snell's law here. And we'll be doing this for red light as well. And we can sub in values for blue light in particular. We know the original medium is air with an index of refraction of 1.003, and the angle of incidence is 40 degrees. Divided by the index of refraction for the glass prism, which for the blue light is 1.47. We're going to do the same for red light. Only one difference here. So the index of refraction for medium number 1, which is air, is 1.003. And the angle of incidence is also 40 degrees. But the index of refraction for red light in this glass prism is not 1.47. Instead, it's 1.46. So they told us that the index of refraction for blue light is 1.46. Apologize, got that wrong. 1.47 for blue light and 1.46 for red light. Okay, let's punch these values in and find the angles of refraction for blue light and the angle of refraction for red light. If we calculate this for blue light, we end up with 25.9 degrees. And if we do the same calculation for red light, we end up with 26.1 degrees. Therefore, the angle of refraction at the left boundary of the prism of blue light is 25.9, and the angle of refraction for red light is 26.1. In part B, we want to calculate the angle of incidence for blue light and red light at the boundary of the prism. So it requires us to analyze a bit of a diagram here. So our original diagram has a triangle, looks like this. This is 90 degrees. This is 60 degrees. We have light traveling in at an angle. We'll start with blue light. When it travels in, it bends towards the normal. And then it will hit the right interface. And we want to know the angle of incidence, which is this angle right here, which I'm going to call theta 3. Okay, so we're going to use trigonometry to determine what this angle is, and knowing our relationship between these triangles and the angles within them. Now, there are several different ways to do it. I've solved it a couple different ways. But for this example, we can use trig to solve for theta 3 for the blue ray of light. And theta 3 is equal to 60 degrees minus theta 2. And theta 2 is this angle right here. We know that theta 2, from our example up above, is 25.9 for the blue ray of light. 60 minus 25.9 gives us a value of 34.1 degrees. We're going to do the same for red light. The only thing that changes is theta 2 for red light, which we calculated above, and we said was 26.1 degrees. If we do the subtraction, 60 minus 26.1, we end up with 33.9 degrees. Therefore, the angle of incidence at the right boundary of the prism of blue light is 34.1, and the angle of incidence for red light is 33.9. In part C, we want to calculate the angle of refraction for blue light and red light as they now exit the prism. So if we look at our diagram here, this blue light ray at this right interface will exit the prism, and it's going to bend away from the normal. And what we want to find is theta 4. We're going to use Snell's law, which tells us that theta 4 is equal to the inverse sine of n 3 sine theta 3 over n4. So that's the inverse sine of, we're looking at the glass prism 1.47. The angle of incidence we just determined up above is 34.1 degrees. And we know that since it's emerging back out into light, or into air rather, that the index of refraction in air is 1.0003. So the angle of refraction for blue light is 55.4 degrees. We'll do the same for red light. So the index of refraction, the inverse sine is equal to the index of refraction for red light, 1.46 times the angle of incidence, which we calculated above was 33.9 degrees, divided by 1.003. If we punch this in, the angle of refraction for this red ray of light as it exits the prism is 54.4 degrees. Okay, our next section is the concept of total internal reflection, or total internal reflection, yes, just like I said. So total internal reflection is an effect that occurs when light encounters a boundary between a medium with a higher index of refraction and one with a lower index of refraction. And we introduce the concept of a critical angle. This is the smallest angle of incidence at which a light ray passing from one medium to another, less refractive medium, can be totally reflected from the boundary between the two. And we can find the critical angle. It's equal to N2 over N1, where N1 is the starting material, which is more dense, and N2 is the second material, which is less dense. And that is a special condition. So we need to go between a boundary, a medium with higher index of refraction, to a medium with lower index of refraction. So we'll write that down. From high index of refraction to low. That's the only way we'll get this phenomenon called total internal reflection. So what we want to find is the critical angle for light passing through water. The index of refraction is 1.33, into air, the index of refraction of 1.0003. So we're going from high to low, so we can get total internal reflection, and total internal reflection happens at the critical angle or greater, and we want to find this critical angle. We know that sine of the critical angle is equal to N2 over N1. So the sine of the critical angle is equal to the inverse sine of N2 is air and N1 is water. So it's equal to the inverse sine of 1.0003 over 1.33. If we punch this in, we end up with a critical angle of 48.8 degrees. That means that if light travels from water to air at 48.8 degrees or greater, then that ray of light will not pass through. It'll be totally internally reflected. In part B, we want to know what happens when an underwater swimmer looks towards the surface of water-air boundary at an angle of 40 degrees, at an angle of the critical angle from part A, which we found out was 48.8 degrees, or an angle of 60 degrees. Let's start with 40 degrees. A path of light ray is reversible, so a light ray that reaches a swimmer's eye must travel the same path as a light ray that leaves a swimmer's eye. The angle of 40 degrees is less than the critical angle. So 40 degrees, since it's less than the critical angle, we're not going to get total internal reflection. What's going to happen is the light ray directed from the swimmer's eye to the surface at an angle less than the critical angle is going to pass through the surface. It's not going to be internally reflected because it's smaller than the critical angle. When light travels at the critical angle, towards the surface, the swimmer will see light traveling along the surface when she looks at the critical angle. So let me just explain what that means. Here's the interface between water and air. Here's the normal. If light travels at the critical angle, theta c, none of the light is transmitted. Instead, it's going to travel along the surface when you look at it at the critical angle. For any value greater than the critical angle, for example, 60 degrees, which is greater than 48.8 degrees, if light travels at 60 degrees, it's going to be internally reflected. None of it will pass through. It'll be reflected, and the angle of reflection will be 60 degrees. Okay, a few things for homework. Practice problems on page 1.6 or 449, 1 to 6. Practice problems page 452, 1 to 3. Practice problems page 457, 1 to 4. And review problems page 458, numbers 1 to 13. I also want you to read up on these applications of refraction and total internal reflection, especially fiber optics, how fiber optics use total internal reflection and what their applications are in society. Thanks and good luck.